Dear students, welcome to the course Verilog HDL. Okay. In the previous video, we begin with the module 2 concepts, beginning with lexical conventions, right? White spaces, comments, strings, operators, number specification, keywords, and identifiers, right? So today we'll see the second basic concepts of Verilog, that is data types. Okay. Before we discuss the data type, we'll consider the value set. What are the values a data type of a Verilog will support? And it will have many data types. So we'll be discussing this in two parts. So today we'll discuss the first part. So first we'll take up what is logic value set. Okay, different values and strength values. Then these are the data types we have in Verilog: nets, registers, vectors. Numbers, they are integer and real. Simulation time, arrays, memories, parameters, and strings. Okay. So out of these data types, so the first three, the nets, registers, and their vector form. So these three will be used frequently in our programming and in our curriculum also. Remaining will be using it, but not that much frequently. So that we'll consider in the second part. Okay. So we'll first see logic value set. So Verilog supports 4 values and 8 strengths to model the functionality of real hardware. Okay. So as we mentioned earlier, so Verilog is not like just programming language, right? To take some values. Okay. So it is a really modeling the real hardwares. Okay. So that's why it supports here 4 values. So what are those values? 0. So 0, it is a logic 0, or in Boolean form it is called as false condition, will be represented as 0. 1, logic 1, or it is a true condition. So along with these two values, other two values are required to model the actual hardware circuits. Okay. That is X, unknown logic value, and Z, high impedance floating state. So next, strength levels. In addition to logic values, strength levels are often used to resolve conflicts between drivers of different strengths in digital circuits. Every electronic circuits, okay, like printer, scanner, okay, whatever you connect to your PCs, okay. So they will be are nothing but having the drivers. Okay, so drivers mean very lowest level will be describing the hardware, right? So there exactly to differentiate the strengths. Okay, so these different strength levels are used here. We'll see what are those in Verilog. So supply, okay, so whatever we give power supply, okay, so 0 to 5 volt or 12 volt, whatever, so that will be the strongest degree strength. Okay, and it is the driving one, okay, type. Okay, similarly strong drive. So this is the strongest and this is the weakest. Okay, so in between it's a degree of strength will decrease. So then we have strong. Okay, so it will be denoted as ST. So you'll be seeing this in simulators. Okay, so by default values it will be taking. Okay, full, large, weak, okay, medium, small, and high impedance. Okay, so out of this large, medium, and small is used as storage type, high Z is high impedance type, and remaining are driving type. Okay, and this is the high impedance will have the weakest strength level. Okay, so how we interpret these strength levels? Okay, just we see an example. If two signals of unequal strengths are driven on a wire, the stronger signal prevails here. Okay, so both may be having the same values or a different value. For example, if two signals of strength, strong 1 and weak 0 content, the result is resolved as a strong 1. Although 1 and 0 is there, definitely 1. Okay, but strong 1 is there, weak 0 is there. Then when we are considering input, so weak 0, strong 1 will be taken. Okay, so these are the contradictory will happen at the driver level. Okay, so to resolve that, so we will be using this. Similarly, if two signals of equal strengths are driven on a wire, the result is unknown. Okay, so for example, if two signals of strength strong 1 and strong 0 conflict, so both are strong 1 and 0, so there is a conflict. In that case, the result will be considered as unknown. Okay, X. Then strength levels are particularly useful for accurate modeling of signal contention, metal oxide semiconductor devices, dynamic MOS, and other low level devices. Okay, so to model these hardware, okay, or issues, these different strength levels will be used. Okay, so in first data type we'll be seeing this. Okay, nets, tri resistor nets, okay, can have storage strengths large, medium, and small. Okay, so this is about the value set. So having knowledge of this value set and the strength levels, we'll now discuss the first data type. Okay, so nets. Okay, so nets represent connection between hardware element. Okay, so just as in real circuits, nets have values continuously driven on them by the outputs of devices that they are connected to. For example, you have an AND gate, right? So how we represent AND gate? So this is the symbol of AND gate. Okay, so it will be having the two inputs and the output is connected to another signal. Okay, so assume inputs B and C are C and output is A. So we'll name this B and C, and this is the output A. So net A will net A is connected to the output of AND gate. So see here. So the output of AND gate. So this is connected, and net A will continuously assume the value computed at the output of gate, which is B and C. Okay. So B and C will have four different value sets, right? So it will take 0 or 1 value. Okay. So if it is 0 0 0 1. Okay. So four different cases it will get 1 0 and then 1 1. So when it is inputted to the AND gate, so what is the function of AND gate? If both the inputs are high, only then it will give high output, otherwise 0. So where that output will be? At the output, and from that output it will drive to the output. Okay, so such cases will use the net data types. Okay, so whatever computed value is there in the output of the gate, that will be displayed. Okay, for example, digital trainer kits you have used, right? You have used the AND gate there with the IC chip. You have connected the inputs to the pins, and the output and outputs you have checked in the LED, right? So as a light, right? So that is where this connection in the hardware or in the programming, we model it as a net data type. Okay, hope it is clear. So nets are declared primarily with the keyword wire. Okay, so the keyword used here is wire. Nets are 1-bit values by default unless they are declared explicitly as vectors. So vectors is the third data type we'll be looking at more here. So at present we'll focus on wire. Okay, some more things. The terms wire and net are often used interchangeably. Okay, although wire comes under the category of nets. Okay, so both are used interchangeably. Okay, so you may be confusing here. So net data type will say keyword by default, it may come to your mind nets, right? But it is not so. The wire keyword, and along with that there are many other, we'll see in the next lines. Okay, so the default value of a net is z. So this is another difference. Okay, future of the net. So by default, when you connect it to the output, so by default any input is not given any values, so by default it will have the z. Okay, except the tri register net. So there is a classification in nets. So in the tri register previously also mentioned, that will have x value. Okay, other than that all will have the z value. Nets get the output value of their drivers. If a net has no driver, it gets the value z. Okay, so driver should be connected. If it is not so, z. So net is not a keyword but represents a class of data types such as wire. So wire is frequently used, so that's why wire I have shown. Along with that, WAND. Okay, wire and WOR. Okay, try, try or try register, etc. So all these data types are comes under the category of nets. Okay, so that's why it is interchangeably used. The wire declaration is used most frequently. So now we'll see the example here. Wire A means what? Declare net A for the above circuit. Wire B comma C. Okay, that means declare two wires BC for the above circuit. Okay, so declaring as a net data type. Even as in C program, you are writing int A equal to 10. Declaration along with assignment. Same way also you can do it in Verilog. wire D, which is equal to 1 bit 0. By default, what is the value of nets? It is Z, except try register. Okay. So, but if you initialize it to 0 now, so it will take now value 0. Okay. So in some cases we require this situation, then we'll assign 0. So net D is fixed to logic value 0 at declaration. Okay. So this is about the nets data type. Okay. So hope it is clear. So the keyword is wire here and it is a scalar. So vector type, we'll see it in the third part. Okay. Second data types, registers. Okay. So there is a clear cut differences between nets and registers. They are like exactly contradictory. Okay. So nets will not store any elements, whereas registers represent data storage elements. Okay. They are not hardware registers. Okay. So they contain the value for a longer period of time. Okay. So we'll see, we'll come to know. Registers retain value until another value is placed onto them. Okay. So until a new value comes, so it will hold the value for such a time. Okay. That's why the name register. Do not confuse the term registers in Verilog with hardware registers built from edge-triggered flip-flops in real circuits. Okay, so actually in microprocessor kits, we will be having registers like serial in, parallel out, serial in, serial out, parallel in, parallel out, parallel in, serial out, like different shift registers are there. This is not that register. Okay, so do not confuse with that. In Verilog, the term register merely means a variable that can hold a value. Only this is the definition. Okay, variable that can hold a value for a certain period of time is declared as a register. Unlike a net, a register does not need a driver. In net, compulsorily something should be connected to that. Okay, so driver. Here, that is not the case. Okay, Verilog registers do not need a clock as hardware registers do. Okay, it does not require any clock like in hardware circuits. Value of registers can be changed anytime in a simulation by assigning a new value to the register. Okay, so just you can change the value, you can do that. Register data types are commonly declared by the keyword REG. Okay, so nets data type using wire, and this is REG. We have used this in previous example, ripple carry counter. Hope it is remember, right? But you don't know at that time. So now we are learning about this. Okay, so it is REG, which will be normally frequently used in test bench programs. Okay, the default value for a register data type is X. This is another difference between nets. Sometimes they will tell you what is the difference between nets and registers. So some of the differences we know. So it does not require a driver. Net requires a driver. Similarly, default value for net data type is Z except try register, and here it is X. Okay. So these are some of the few differences you can note down between nets and registers. So example of how registers are used is shown below. Okay. So register is the keyword, reset is the variable. So declare a variable reset that can hold its value. It will be used in a part of the program. It is shown here. Initial, begin, reset equal to 1 bit 1. Okay. Previous example we have used it like this. This construct will be discussed later. Okay. So don't bother about this. In behavior description, we will be learning about this initial always and all. So just we are learning now how register will hold a value. So now it is 1 bit 1, and at 100 time units we are changing the reset to 1 bit 0. That means from 0 to that 100 time units it should hold a value, right? That's why this is declared as a register here. If you declare here wire reset, then this may not work properly. Okay, so that is the meaning. Registers can also be declared as signed variables. Such a register can be used for signed arithmetic. Okay, so along with register keyword, if you use signed keyword, so it will be used for signed arithmetic. Okay, and this 630 is vector part. We'll be looking at in next data type. Okay, so integer I. Okay, so 32-bit signed value. So you can write register integer I. Okay, so it will be the integer here in this signed arithmetic. So like that also you can modify the register data type. So as we use in the program, so you'll be familiar with this. Okay, so this is about nets and registers, very basic data types we'll be using frequently. So now both this nets and register, what we declared, it is a scalar. That means only one bit we have done. So now there is a group of bits we need to use a vectors. Okay, nets or register data types can be declared as vectors. That means what? Multiple bit widths. Okay. If bit width is not specified, the default is 1 bit, right? That is called as scalar, what we have used in wire and register. Vectors can be declared at So this is a very important one. Okay, there are two types of machines. Based on that, either one we will use it, little endian or big endian. Okay, so high low or low high fashion we can represent that. Okay, but here the first one will be the MSB, most significant bit. Okay, and this one will be the LSB. Okay, so least significant bit. And here also high is there, means here low is there, it is not low LSB. Here also the first one is MSB. Most significant bit is 0 here, least significant bit is whatever number. Okay, that is the idea. In the example shown below, bit 0 is the most significant bit of vector virtual address. Okay, so here we have defined that virtual address, so I will explain that. Example here, y array, there is a scalar. Okay, only one, there is no size. If the same thing, if you write high number and low number, so with this fashion, so MSB is 7, LSB is 0. Okay, so for example you have the widths. Okay, so 7 6 5 4 3 2 1 0, 8 bit. Okay, so 8 bit bus represented like this. Okay, then wire 31 is to 0, bus A, bus B, bus C. Okay, all the three buses of 32 bit width. Okay, in digital electronics number starts with 0, so that's why 31 means 131 plus 132 bit, it will be the width. Okay, so square brackets are used, and then any one fashion will be used here. So in all this high fashion is used. Next, register clock with respect to register data type, so it is a scalar register, only one bit. So same thing, we will write it in another fashion. So low number and high number, so this is the second one. Okay, so here 0 is the MSB bit and 40 is the LSB bit, and this data type identifier name is virtual address. This is the keyword identifier, and this is the specification of vectors. Okay, so what is the width? Same, 40 is there, so 0 to 40 means total 41. So vector register virtual address 41 bits wide. So this is how we understand. Okay, so some more things regarding vectors. Vector part select. For the vector declaration shown above, it is possible to address bits or parts of vectors. Okay, so whatever we have done, part of the vectors we can refer in the program. For example, bus we have defined as 8 bit, right? So only in that, so if we mention like this, only one, only the 7th bit we can use, bit number 7 of vector bus A, only that we can refer in the program to change it or modify it. Then similarly, in a bus of 32-bit bus, I'm referring only the lowest 3 bits. Okay, 3 least significant bits of vector bus. Okay, using bus equal to 0 to 2 is illegal here. So in the previous example, we have declared, right? So the net 31 is to 0 bus of wire data type, right? So where we have considered the first notation, high number, low number. So then in referencing that in the part select, you should not use reverse way, low number, high number. That is illegal. Okay, because the significant bit should always be on the left of a range specification. Whereas in this case, virtual address 0 is to 1. Here it is mentioned low number, high number. That's why 0 is to 1 is valid. So it indicates two most significant bits of vector virtual address. So out of 41 bits, only we are referring the 2 MSB bits. Like that, we can select part of the vector. We can select that, we call vector part select. Okay. Finally, we will see the variable vector part select. Okay, so another ability provided in Verilog HDL is to have variable part selects of a vector. So these are the additional features which will be used, but in our programming up to the vector register data type, if you know, sufficient. Okay, but this should be known as a programmer. So what is this capability? We'll try to understand. This allows part selects to be put in for loops to select various parts of the vector. So there are two special part select operations. Okay, so one is you can write starting bit and then a plus sign and then width. Okay, so starting bit you can write, so how much you have to add, so that is the this one, part select increments from starting bit. So we'll understand this with an example, you will be clear. So this is the syntax. Okay, similarly you can have starting bit minus sign width. Okay, part select decrements from starting bit. Okay, so this can be written in reverse fashion for another. Okay, so you can specify width this side, starting bit minus. Okay, like that also you can see. The starting bit of the part select can be varied, but the width has to be constant. Okay, so that can be varied, but width will be constant. The following example shows the use of variable vector part select. So from example, it is clear to you this concept. So this is the example. Okay, so clearly give attention. So we have used here two variables, data 1 and data 2. Okay, one of little endian notation. I told you two types of computers are there. Okay, so little endian, big endian. Okay, so one will use the highest as the MSB, one as the lowest as the MSB. Okay, then register 7 is to 0 byte. Okay, so this we are using a variable part select. One can choose parts. Okay, so this bit it is 8-bit. Okay, so now we will refer variable part select now. So byte data 1, which is 255 to 0. In that I'm writing here starting bit is 31, then minus sign, width is 8. That means what? Starting bit is 31, decrement 8. So 31, 30, 29, 28, 27, 26, 25, 24. So what will come? 31 is to 24. Out of 32, only you can refer the 8. So that you can represent like this in program. That is the capability of Verilog HDL. Similarly, increment. So 24 is the starting bit. Add it 24 to 8, 25, 26 like that you will get 31. But writing is same because this data 1 is declared as 255 is to 0. That's why declaration should be like that. So here starting bit will come here 24. It is incremented. No, this should be written this side only. Okay, otherwise illegal. Similarly, we'll see with the second one, big endian notation. Data 2 we have considered 31 minus 8. So in this case, starting bit is 31. So width is 8. You have to decrement it, but you have to write 24 first. Clear? Because it is 0 is to 255 fashion. So this will be the starting bit and this is the end bit. Similarly, 24 plus 8. So 24 is the starting bit. Bit is added. So in this case, it will not change. So 24, 8 will be added, 31. Clear? So minus sign here it will complement. Here plus sign it will be get reversed. Okay. So this should carefully manipulate. Okay. So the starting bit can also be a variable. The width has to be constant. Therefore, one can use the variable part select in a loop to select all bytes of the vector. So this is how we use it. So now we'll see an example in for loops and all how we use. So more don't crack too much. Okay. So we'll be understanding this later. So for j equal to 0, j less than or equal to 31, j equal to j plus 1, only part we have to select. Okay. So what is that part? So byte data 1 is equal to j star 8 plus 8. So 0 is to 8 is 0, 0 plus 8 is 0 to 7. So 7 is to 0, 15 is to 8. Okay. So like that you can consider 23 is to 16. So like that you can select a group of 8 bits in the 255 bit. Okay. That we can do it like this. Similarly, this is another example. Okay. So it may not be, it is a part of a program. Okay. Written over here. So this is it regarding the first part of data types. Okay, so we have seen the value sets. Okay, it will have 4 values 0, 1, x and z, and then 8 different strength levels are there, strongest to weakest. And then we have seen the data types nets. Okay, it will be declared using a keyword wire. Default value is z, and here there is a driver should be connected to output of that. Okay, so second type register. So it will be declared using a keyword reg. Its default value is x and it does not require a driver. So it is a variable that can hold a value. And then vectors of multiple widths to specify, we will use vectors for wire, register, or any other data types. Okay, so there are two notations are there. Normally we'll use the little endian notation frequently in the program. Okay, so this much for today. So in the next video we'll be looking the remaining data types. Okay, thank you.